the infections models to epidemic models. So the equations will be differential, since the number of the people is quite large. So the epidemic process is continuous as people meet each other and they infect each other with time. So it is the continuous process, and it's okay to say that the number of susceptible. So susceptible means people who can get sick, that are not immune and that are not sick at this moment. So it is our S depending of time t. It is the continuous function. I, it is the number of infected at current moment. And R means the number of recovered or immune. Depending on the model, the number of recovered means the number of people who are not sick at that moment, who was sick, but it's okay with them and they get some immunity. Or otherwise, if we consider, for example, AIDS models and some more severe diseases, we can consider this as removed. So the people who die from the infection, and therefore they do not infect anyone. So the simplest model, the most simple one, it is SIR model. It was introduced by McKendrick by Kerman and McKendrick in 1920s. So the model is have quite large history, quite long history. So the interaction between susceptible, infected, and recovered is directed by the following formula. So all the individuals that are susceptible can get infected, and then at some time they can become recovered and removed, depending on the model. So what are the equations that derive these transitions from susceptible to infected and from infected to removed? What is the mechanism of infecting? How does susceptible become infected? We understand that the probability of being infected depend on the product Si. So S dot depends on the susceptible number and the number of infected. It's quite natural. That's why when the epidemic begins, we are trying to decrease the susceptible number or decrease the infected number. So some isolation ideas decrease the number of infected, and something like quarantine also decrease the number of susceptible. If everyone is sitting home, the product Si will quickly decrease. That was the way we were trying to fight coronavirus. The work from home and so on. So it is everything. It was not S dot, it is I dot. I'm sorry. It is the product of I will depend on Si. not the product. Well, the I dot. And if we consider the disease like flu or something like this, there is some coefficient that that is responsible for transition from I to R. For example, if we consider the simple flu, it is like 1 week, 1 or 2 weeks. Usually after a week, everyone who is sick becomes recovered and immune. So a few more words about the coefficients. So so far, every member of the population typically progress from susceptible to infected and to removed. There is the transition coefficient, beta as the contact rate. So since we consider the meeting between S and I, for example, you are susceptible and you are going in one train with infected, there is some probability for you to be infected. So this is our beta, and we consider that it is a constant as some average probability to be infected. We understand that these contact between S and I, these contacts are different. Some of these contacts last all the day. If, for example, one of your group mates is infected, so you contact them all the day when you go lections and practices. So and some of possible contacts are short. So beta, it is some average contact rate. Next, the transition between I and R. The transition rate, it is our gamma. It is some speed of the recovery or death. And if we consider the duration of the infection as D, it is the time, the average time of being infected. So gamma usually is taken as 1 divided by D. So for flu, it is 1 divided by 15 usually. And for it is an interesting problem how to understand what is the duration of infected for long diseases like AIDS, for example. Some calculations shows that people, the average lifespan with AIDS can be more than 10 years. So if an individual takes curation, the AIDS do not affect the life expectancy, so it can be more than 70 years. And if he doesn't take curation, the life expectancy is very short. It is close to 5 years if there are no additional deductions like drugs and so on. So this gamma is a constant, but the constant depends a lot on the disease, on the nature of disease. So far, what is the equation? The equation. the differential equation of Kermack and McKendrick is the equation 6t. So it is the transition S to I to R, and the first one, it is the transition from S to I. We see that the number of susceptible in this model always decrease as beta and gamma are both positive. We see that S dot is always negative. It is always negative, so the susceptible number is usually decreased. Is decreased all the time. It means that everyone of susceptible can become infected, but we'll see further that not all the susceptible will be infected at some moment. Next transition, it is the last one. It is the transition from I to R with the rate gamma. So all the infected becomes recovered at some time. So if there are no susceptible, we see the differential equation I dot is negative gamma I. So far, if there are no susceptible, the number of infected is decreasing exponentially, like this. And with the rate of gamma, we see that the number of infected will be decreased at e times. So triple decrease at one period of time. So the most interesting equation, it is the second. It is our epidemic process. So the I dot depends on the positive increase of the infected number and decrease of the infected number with time. So we can analyze the second equation. Let's look at this. We can rewrite it in the form I multiplied by beta S divided by N minus gamma. And the N, it is the sum of S, I, and R. We consider it constant. So let's try to understand what can the last equation give us. We see that the differential of I will be positive if the quantity is greater than 0, and it is negative if the quantity is less than 0. So the usual solution of our equation looks like this. So blue, it is the susceptible number. Red, it is the removed or recovered number, and green, it is the infected number. So returning to previous formula, we see that I dot is positive if and only if S is greater than gamma n divided by beta. So if the susceptible number is big enough, then the epidemic increase, and the epidemic decrease if and only if S is less than gamma divided by beta n. And we see, since S is decreasing, then we can prove that at some moment, S will cross the borderline, and then the infection will stop. We see that I is growing up to some moment. At that moment, S of it is our time t est. At that moment, S is gamma n divided by beta. And then after that moment, the number of susceptible is growing down, and the epidemic quickly ends. And usually we see that not all susceptible become infected. There is some positive quantity to infinity at the infinity moment. What more? Yes, I said that since if we calculate the sum of our differentials, or the sum of the left-hand side and the right-hand side of the equation, so we can just add this plus this and plus this. So to the left we see S dot plus I dot plus R dot. To the right we see 0. So when we integrate it, we get this formula. So the sum of susceptible, infected, and recovered is a constant. And another important thing, we introduce the ratio R0, and we call it basic reproduction ratio. It is the number of new infected from a single infected one. We can see that the estimates for coronavirus were something like 5 for COVID. It means that everyone who is infected infects average 5 person. It's quite big number. The number is quite big, and that's why the infection was so widespread, and it was very hard to stop. What is next? What is next? We can get some more analysis from the model. A few more words. We can say that the typical time between contacts is 1 divided by beta, the typical time until recovery, it is 1 divided by gamma, and therefore the basic reproductive ratio is the division between these times. Recovery divided by typical time between contacts. One more thing, we can consider the first and the third equation, and we divide first by the third. Let's do it. If we divide the first by the third, we get ds divided by dr is negative beta s divided by gamma n. And we can integrate it as S of R. After an integration, we get the following formula. The initial moment we consider 0. And the initial values are S of 0 and R of 0, the initial number of susceptible and removed. So it is our formula for susceptible and removed. And next, after taking the limit of time going to infinity, we can derive that at the end, the proportion of recovered individuals follows the transcendental equation. The transcendental equation. And if S of 0 is not 0, then R infinity is not equal to n, and it means that after end of epidemic will remain some susceptibles. So not everyone in the population will get sick. And we see it in the historical epidemics when R0 was quite large. The same, there was some number of people who were not sick. What more? We come back to our second equation. We can rewrite the second equation in this form using our R0. And finally, we can see that that the main this main fraction n divided by s of 0, if our basic reproductive number is large enough, then the epidemic outbreak occurs with an increase of the number of infected. And on the contrary, if R0 is small, then there will no outbreak, and our I will just decrease with no outbreak. It is I. So if R0 is less than n divided by s of 0. This case, and with epidemic outbreak, like this. It is the situation when R0 is greater than n divided by S of 0. So the basic reproduction number is extremely important. Is extremely important. What more? Well, a few more words about the simplest model. About the simplest model, since the condition of epidemic outbreak is R0 is greater than n divided by S of 0, what can we do to fight the epidemic? We have to decrease S of 0. It's not that easy to understand, because usually we are trying to decrease number of infected, but it doesn't give us the proper result, because we see that the epidemic outbreak does not depend on the number of infected. It's the most important thing. So it doesn't mean how many infected there are in our population. Everything depends only on the number of susceptible. And we have to decrease the number of susceptible. If we decrease it lower than n divided by S of 0, then we can stop our outbreak. For example, let us see, if for COVID R0 is 5, then there must the susceptible number must satisfy the following equation. So S0 must be less than 20%. That's why the officials were trying to decrease the number of the people who are going out of their houses. So they stopped some public activities. They stopped anything that need a lot of people that are at one place at the same moment, and so on. But we see that for COVID, if R0 is 5, it's really very hard to decrease S0 below 20%. Extremely hard, because nowadays people are active. People spend a lot of time outside. People love to interact each other, not using the communication systems, but themselves. That's why the officials really failed to fight coronavirus. So they just a little stopped this peak of the infection. Maybe just a moment. So if the theoretical peak is like this, with the high number of infected at the same moment, and after quarantine restrictions and so on, it is something like this. So the time of this peak is moved to the right, and the peak itself is less than theoretical one. So if the capacity of our hospitals is, for example, here, we can see that the theoretical peak is higher than the possibility of our medicine, and that means that a lot of people will die at this peak because they can't get proper help. So that was the main idea of our officials, to decrease the peak of the infected number below the possibilities of our medical system. That's the main idea of these analysis. Well, there is a lot of expansions of SIR model, a huge number of different expansion. First of all, what should we consider? What should we consider? If the disease is long enough and it lasts for ages, like AIDS, for example, then we have to take into account the death rate in our population, the death rate of in all cases. So it is just the death rate for all of them, for susceptible, infected, and recovered. And these death rate do not depend on epidemic. It is all the possibilities to die in accident, from the age, and so on, from non-epidemic diseases. And we must take into account the fertility coefficient. So lambda, it is our birth rate. And the modified equation takes the form 61 with a death rate and birth rate. And we see that this model, the previous one, the SIR model without birth and death rate, there were no disease-free equilibrium. So the only equilibrium in the previous equation was 0, 0, 0, that there is no epidemic at all, or 0, 0, no, that depend on the initial values. So everyone is susceptible. It was the disease-free equilibrium. And now, in this model, the disease-free equilibrium, meaning that there are no infected, it is our lambda divided by mu from the first equation, and I and R as 0. And for this model, we can rewrite our basic reproductive number in the following case. So it's just derived from the second equation. And for this case, we can see that if our R0 is small enough, then our model is going to disease-free equilibrium. So the epidemic ends, and the number of the population. So at the end, the susceptible number is lambda divided by mu. So the birth and death are balanced, and there are no infected and there are no recovered at the infinity moment. But if R0 is greater than 1 and the I of 0 is greater than 0, then there can exist positive solution that is called endemic equilibrium. Endemic equilibrium. And it means that in some cases, the disease will remain in the population forever. So there will be some number of infected at every time. There will be some number of recovered at the same time, and there will be some number of susceptible. And we see that there are some diseases that circulate through the population, and we can expect that they will remain forever. If, for example, there is no good vaccination, if there are no ways to decrease our R0, then the infection will go to endemic equilibrium. But if we can control our coefficients, if it is possible, for example, well, what do we need? We need to decrease R0. We need to decrease R0. That's why, for example, we can increase gamma. If we increase gamma or decrease beta, then we have the chance of changing from our endemic equilibrium to disease-free equilibrium. And there are some diseases that were beaten by the people community using vaccination, using some prophylactic, and so on. And we can expect that we can fight some hard and severe diseases like AIDS in maybe not nearest future, but in some future with the proper curation, the proper observing of infected, with the decreasing number of susceptible, and so on. So sometimes the endemic equilibrium can be changed into disease-free equilibrium. What is next? What is next? There is another SIS model. SIS model, meaning that the infected does not become immune. So if for SIR model they were going from susceptible to infected to recovered, and here after the infection they become susceptible again, and let gamma is our, as usual, beta is the coefficient that is showing us the rate of infection, and gamma, it is the time of the infection. And so far, all the infected come back to be susceptible. And for sure, we can expect, in this model, we can expect that the disease will remain the same. So, this equation is quite simple to analyze. First of all, because we can find that S is n minus I. So S is n minus I. And we can rewrite the second equation in the following form. So far, we see that the infection is ruled by some kind of logistic equation. And we analyzed the logistic equation in previous lections. And finally, we see that there are two equilibriums, the zero solution and non-trivial solution. And we have the same R0. And we expect that if it is small enough, then the infection will end. And if it is big enough, then the infection will remain. It's not that difficult to prove. What do we see? If beta n divided by gamma is less than 1, we see that both these and these are negative. Both of them are negative, and I dot is always negative. So far, since I is decreasing, it will decrease to 0. And if beta n divided by gamma is greater than 1, then the first is positive, the second is negative. So finally, they will balance each other. And there is the non-trivial equilibrium I equals to n minus gamma divided by beta. So the same, like n minus R0. Well, quite simple equation and simple analysis. And moreover, one can find the exact solution of the equation using the substitution I equal to inverse y. And finally, the solution, the general solution of the equation is given in this form with some constant I infinity and x and v. And using the equation for S, we can get the all exact solution. One can prove that for two these different situations, the limit of I of t is 0 or n minus gamma divided by beta. You can prove it by yourself. It's not that complicated. So there is the exact solution. Next, there is another model with some death rate. We can consider the our epidemic model with some number of individuals who die in case of the infection, and we can make the same analysis of our equation. So as usual, our SIR model, but with the mortality. We can say that this equation is quite good for COVID. in COVID, we see that there is some small amount of death. For COVID, it is close to, as far as I remember, 3% of infected dies. So more than 90% recovered. And we can use our numerical calculations to understand how many will die and how many will recover. There is some more classes of the epidemic equations. The epidemic equations because, for example, the MSIR model, there is some number of newborns that can be immune as for the first few months of their life, they are protected from maternal antibodies. So it is called passive immunity, and we can add this M class of our newborns. So the number of newborns depends on the birth rate, and some of our newborns becomes susceptible in some time. And where is negative mu m? Negative mu m. So they just become susceptible. And mu, it seems that it is our usual mortality for all the people in the community. So it is the model for passive immune of the newborns. Next, there is additional model. Sometimes there are exposed. The number of the infected who are infected yet, but who do not infect others. So they are sick, but they do not dangerous for susceptibles. And there is some incubation period for our exposed. So they become infected. Sometime the infection is developed in the body, and then after some incubation period, they become infected and start infect their susceptibles. So far, the equation for exposed takes the following form. Mu is our usual death rate, lambda is birth rate, and we see that after contact of infected and susceptible, the individuals become exposed. And with the speed a, the exposed become infected. And as usual, one can calculate the basic reproductive number for this case. It will be equal to the product of two fractions, a divided by mu plus a and beta divided by mu plus gamma. There is a really huge number of different models that take into account a lot of features of diseases of the population and so on. But I want to add that there is the main problem for these models. It's really very hard to find all the coefficients. Look at this model. There is the coefficients for newborns. It's okay, we can analyze it. Maybe there is some statistics. There is the death rate. Okay, the death rate can also be analyzed with the statistics. But what is beta? How can we find beta? How can we find A? How can we find gamma? All of these coefficients are derived by statistics. So they are calculated with some precision, with some accuracy. And finally, so we can like beta plus minus beta 0, gamma plus minus gamma 0, mu plus minus mu 0. So finally, R0 is our R0 plus minus some delta. And this uncertainty can be quite large. That's the main problem for our equations. The more features we take into account, the more coefficients we have. And that's the problem itself, how to find these coefficients in the most right form. The analysis for this model can give us the same situation with the disease-free equilibrium when there are no one is sick, and there is the endemic equilibrium. Well, and we can find it using our equation. So we can expect the endemic equilibrium here. It will be very close to previous endemic equilibrium for the model with fertility and mortality, like this. Something close to this, but not the same. Not the same, but can be found in the similar way. What more? What more? There can be another model, SEIS. So our previous SIS model, but with the exposed one. The idea is the same, but in SIS model there was this way of transition, and now SEIS, this way. This way. Next, moreover, we can add the passive immunity. So exposed passive immunity and SIR model. I don't want to focus on all of them because the more coefficients, the more difficult is analysis and you can see that there is a book dedicated to this model. So just a short introduction to this idea. Next one. What more complication we can add? There are a lot of diseases that depend on some seasonal coefficient. We know that flu, for example, flu is seasonal, and it is usual in autumn and in the beginning of the winter to see the epidemic of the flu. So far, we can take into account this seasonal feature. So our beta will be periodic, and the period of beta is 1 year. And there is a lot of different diseases. Some of them correlates with the period of year. Some of them, measles, mumps, rubella. Have no idea what is this, but they are mostly correlated with the school, because the children come back from vacations to school, and the epidemic starts. So we have to consider the periodic beta. And for this case, it is our SIS model. SIS, we can take into account the R0 in the following integrated case. So the same analysis that we made for a constant beta, we can see that this formula is very similar to our system with a constant beta, but now we substitute beta with the average integral beta along the period. And the same, we have the disease-free equilibrium if our R0 is small enough, and we have endemic equilibrium if R0 is big enough. So we can expect the annual or sometime biennial epidemic outbreaks for our disease. And the last model with vaccination. There is a huge number of models with vaccination, but just a simple example. We consider a model for which we vaccinate the newborns, and the vaccine gives the lifelong immunity, like polio, for example. Now, almost all the newborns are vaccinated against polio. The rate is close to 1, and that's why there is almost no problem with polio in Russia. All of our parents are vaccinated. Most part of us are vaccinated, and maybe only nowadays there is some anti-vaccinated community that decrease our P, but the most part of the population of the newborns are vaccinated. So there is the new V class, the class of vaccinated, and we add this vaccinated class. So the higher is P, the less will be this addition to our susceptibles. Mu is our usual death rate, and beta is the rate of the infection. And I think we have to add some recovered from gamma. If we want the sum of S, I, V, and R to be equal to 1, then we have to add an equation for recovered. So we can use the same analysis. First of all, from the last equation, we can see that we can simply solve the equation. It's linear equation, and the exact solution gives us that V is going to NP. So for large period of time, we expect that the number of vaccinated will be equal to the proportional share of the population. If we start vaccinate at some moment, in a long period, the vaccinated number will be proportional to the vaccinated, the strength of the vaccination. And the same, we have the disease-free equilibrium, and we have the endemic equilibrium depending on our R0, And looking at the endemic equilibrium and disease-free equilibrium, we see that the vaccination program will be successful if our vaccination intensity is greater than 1 minus 1 divided by R0. And we see this formula when the vaccination program against COVID was launched. We know that if the number of vaccinated number is greater than 1 minus 1 divided by R0, then we expect the decrease of our epidemic outbreak, and we expect the disease-free equilibrium in future. But what was the problem? The R0 for alpha version of COVID was 2 or 3, and for alpha version we need to vaccinate a half or 2 halves of our community, and for Delta it is like 5 Delta COVID, and then we need to vaccinate 80%, and we see that not all countries reached this number. Moreover, sometimes vaccination is not effective. There is some number of people who were vaccinated, but it doesn't work. There is some number of people who cannot be vaccinated, for example, children, pregnant women, and so on. they need a lot of new investigations, and they take a lot of time. So finally, there is an example. If R0 is 18, then you have to vaccinate 95% of the population to fight the disease. And we know that there is a lot of anti-vaxxers who are against any type of vaccination. And that's the main problem, that small number of anti-vaxxers, they quickly decrease all the effect of our vaccination program. And finally, we can consider the vaccination of non-newborns at some rate. The rate is rho. And then the equation will take the following form. And using all the previous technique, the equation for eradication of our disease will take their final form. For sure, we have to add the equation for infected one. So plus the I dt as in the previous case. Well, that's all about our lections. Now I'm ready to listen your presentations. What about you? Are you ready? Hello, what about your presentations? Is anyone ready?
Seems like there's nobody prepared today.
Wow. And what about the remaining? There is like 60 students, and it seemed that there were only 30 presentations. What about remaining 30? If you want to get a good mark at the exam, you must show me your presentation. Otherwise, the mark maybe will not satisfy you. Well, I think all of you presented the presentation, so just ask your mates to hurry up. We have maybe 1 or 2 more days according to our timetable. So I think you have to fill all of these days with your presentations. Well, if you have any questions, ask me. If not, see you next week.
Bye. Bye.
Thank you.
Okay,
Bye.
bye.